So, the result is broken down into two smaller results. Let us say the first result by we denote by lemma 1. So, the first lemma says that let us have two real numbers alpha and beta such that I have one value, one number less than the other number, let us say alpha is less than beta. Then there exists a function, nu which is second order differentiable over the entire real axis such that nu is positive, and well it is positive for all x inside this interval alpha comma beta, and nu of x is equal to 0 for all x in R minus alpha comma beta, right. So, which means all this lemma says is that for any given real interval I can always construct a second order differentiable function which is positive inside the interval and vanishes outside the interval. And the proof of this lemma is straightforward by assuming the following function. We assume nu is this form, nu is x minus alpha cube beta minus x cube, where x is from alpha to beta and nu is 0 otherwise, right. Okay, we can see that nu is positive inside the interval. So, it checks out this condition, it also checks out this particular condition, this construction of nu, and also we have to see whether nu is second order differentiable, namely the derivative of nu exists over entire R, right. Certainly it exists outside the interval. So, certainly this condition checks out or holds outside the interval alpha beta. So, we just need to figure out what is the first and the second derivative of this function inside the interval alpha beta, right. Okay. So, as I just said, nu of x has all properties satisfied except perhaps nu is not second order differentiable. Well, we are not sure unless and until we have shown that it is second order differentiable, right, second order differentiable. Okay. So, let us now calculate the first and the second derivative of this function. So, the first derivative we can go ahead by evaluating the necessary limits. We see that the limit of this function nu of x minus nu of alpha. So, the limit, let us say limit from the right divided by x minus alpha is x minus alpha cube beta minus x cube divided by x minus alpha, right. We see that this limit is x minus alpha square beta minus x cube, right. And when I take the limit x going to alpha plus alpha from the right, I see that this goes to 0, right. And similarly, when we take the other limit, the limit from the left of nu of x minus nu of alpha divided by x minus alpha, I know that nu of x from the left will be 0 via this definition of the function, right. So, I have that this is 0 minus 0 divided by x minus alpha, or this is equal to 0. So, from here we conclude that nu prime at alpha exists and this is equal to 0. So, similarly, we can conclude by evaluating similar limits that nu prime at beta is also equal to 0, right. So, what we are trying to show is that nu is indeed differentiable up to second order at the boundary points, because in the interior nu is a polynomial. So, that it will be definitely differentiable. Outside the interval it is 0, so certainly differentiable, but perhaps not at the boundary points, right. So, here we have shown that it is first order differentiable at the boundary points. So, similarly we can look at the second derivative. Let us look at the second derivative. Again we have to evaluate the right hand side limit and the left hand side limit of the following ratio, nu prime x minus nu prime alpha divided by x minus alpha, right. So, this right hand side limit is the following. We can easily differentiate. We have already evaluated nu prime of x. We can easily differentiate and evaluate. This is 3 of x minus alpha square times beta minus x square. Again this particular expression follows by direct differentiation of the function. So, there is no complexity involved at all, divided by x minus alpha, and when we evaluate the right hand side limit we arrive at the fact that this is also equal to 0, right. And similarly we can show that the left hand side limit x going to alpha minus of nu prime of x minus nu prime of alpha divided by x minus alpha is also 0. And from here we can conclude that these two statement helps us to conclude that the second derivative of nu at alpha is 0, right. Okay. And finally, we can also do the same thing at x equal to beta. So, similarly we can check that the second derivative of nu at beta is also 0, right. So, what we have is the following. We see that the first derivative, while going through this exercise we have seen that the first derivative of nu is 3 times x minus alpha square beta minus x square beta plus alpha minus 2x, where x is in alpha comma beta and it is 0 otherwise, right. And I have that nu double prime x is 6 x minus alpha beta minus x times x minus alpha square plus beta minus x square minus 3 x minus alpha beta minus x, right, for all x inside this interval alpha beta, and it is 0 otherwise. So, what this expression shows that the first and the second derivative of nu exists, and hence we can conclude that nu is in the class of second order differentiable functions over the space of the real numbers, right, and that concludes the proof of our first lemma. So, we have so essentially what we have shown is that nu is a choice of our perturbation function, right. Let us go back to the slide where we are going to use the lemma. So, this is the choice of our perturbation function. So, let us go back to slide 2 slides back. So, we are trying to show that this holding, this integral of this quantity holding set equal to 0 implies that this function is 0, and we are showing it by a contradiction by finding a particular value of eta. And just now in the first result we have shown that nu satisfies all the properties of the perturbation function, that will be our choice. Okay. Then the second result says the following, which is actually the statement that we are after. So, the second result says, suppose I have that the inner product of the perturbation eta with respect to g, any second order differentiable function g is 0, where eta is a perturbation, an arbitrary perturbation, and well, and I have that g is a function from x 0 to x 1 to r, is a continuous function such that g is identically well. Again, so what the result says is, suppose the inner product is 0 for all such perturbations, where g is a function which is continuous function, then so not this one, then I must have that g is identically 0, g is identically 0 on the interval x 0 to x 1, right. Okay. Again, the proof is very straightforward. Once we have shown the result in the first lemma, the second result is very straightforward. So, without loss of generality, we assume that well, first of all, let us the first statement of this proof will follow the fact that we assume that this holds, right, this holds, but g is non-zero, right, and we will show some contradiction. So, to do that, let us say that g is non-zero for some point c in the interval x 0 to x 1, and then without loss of generality, let us further assume that g of c is positive, right. We could always assume g of c is negative, does not matter. So, let us say that g of c is positive and c, so c is a number from x 0 to x 1, then what I have is, since I am given that g is continuous, I know that g is a continuous function. So, since g is continuous, which means that there exists a neighborhood of c inside this bigger interval where g will be positive, right. So, that comes from the continuity. Since g is continuous on the interval x 0 to x 1, right, it implies there exists two numbers alpha beta, right, alpha beta, such that this holds x 0 less than alpha less than c less than beta less than x 1, right, and g of x is positive for all x inside this interval alpha comma beta, right. Okay. So, what we have done is, we have found an open interval alpha beta where g is non-zero. Then the moment we have a non-zero function inside an interval, we can invoke our first result. We can invoke our lemma 1. So, by lemma 1, it implies that there exists a function nu which is second order differentiable, and nu is positive for all x inside the interval alpha beta, and nu is 0 for all x from x 0 to x 1, right, minus the values inside the interval where nu is positive, right. So, which means that nu is the set of belongs to the set of perturbation functions. So, my H is the set of perturbation functions, right. So, nu belongs to the set of perturbation functions, and the inner product of nu with respect to g, which is the integral from x0 to x1 nu times g dx, which will be equal to the integral from alpha to beta, because outside this interval nu is identically 0. So, integral from nu times g, I know that this particular integral is positive, right, because g is positive, nu is positive. So, over this interval the integration must give a positive value, and hence we have arrived at a contradiction, because we have assumed that this particular integration must be equal to 0, right. Okay. So, what I have is, let me just summarize all our results so far. So, by lemma 1 and 2, what I have found is, if I am given that the inner product of eta with respect to E, where eta is the perturbation function, is 0, it implies that E is identically equal to 0, right, which is our necessary condition for extrema, necessary condition for extrema. Okay. Okay, so let us now recap. Let us now recap our entire discussion over the last 1 hour, roughly 1 hour, in the form of a theorem, which is the most important theorem of this entire course. So, this is my summary. So, the result says that suppose I have a functional which is a map from the set of all second order differentiable functions to the space of all real numbers. So, this be a functional right of the form j of y is equal to integral from x0 to x1 f of x comma y prime dx, where f has continuous partial derivatives of second order. So, the integrand has continuous partial derivatives of second order with respect to the variables x, y, y prime, right, and I have that x0 is less than x1, and further let my set S be the set of all second order differentiable functions x0 to x1, such that y of x0 is y0 and y of x1 is y1. So, fixed endpoint functions. Then the result says, if y in S is an extremal, it must satisfy the equation as follows. It must satisfy this particular equation, which is our expression E that we have just shown earlier. So, del d dx del f del y prime minus del f del y equal to 0, and again this is the most important results which we are going to look at in more depth over the next several lectures. So, let me call this as our result 4. So, 4 says that, well, what we see is that 4 now is a differential constraint. So, it is a second order non-linear ODE that any smooth extremal must satisfy, right. So, second is so the equation 4 is a second order non-linear ODE that any smooth extremal y satisfies, right, and that is also the necessary condition that I just said, and this is further known as the famous Euler Lagrange equation. From now on I am going to talk about this equation and denote it by the shorthand notation EL equations. Okay. So, it is the infinite dimensional, note that this is the infinite dimensional analog of, so infinite dimensional analog of the condition grad f is equal to 0, for which was the condition for the finite dimensional case, the finite dimensional calculus case, right. So, this is just like the first derivative test in the finite dimensional case. Okay. So, before we wrap up this discussion, let me just show you the application of this particular expression, how we figure out the extremal function of any functional. So, my first example involves finding the geodesics over a plane, geodesics on a plane. Again, students, please recall that geodesics on a plane will involve finding the shortest. So, this particular problem has been described in the previous lecture. So, it involves finding the shortest path between the points. Let me now fix some points. Let me say that my first point x 0 y 0 is, let us say for example 0 0, and my second point x 1 y 1, let us say this is 1 1. So, I am just fixing some points randomly, right. So, we have to extremize, given these fixed points, we have to extremize j of y, which is the functional from x 0, which is 0, to x 1, which is 1, of the total arc length of the curve, which is 1 plus y prime square dx. So, this is my arc length functional. Now, so which means to find the extremum, I have to satisfy the Euler-Lagrange equation, and note that, again let me first write the Euler-Lagrange equation and then it is easier to see how it simplifies. Okay. We see that where f in this case, f is the integrand 1 plus y prime square. We see that f is independent of y, f is only a function of y prime, which means I can, in this particular case, I can certainly for certain say that this partial derivative of f with respect to y is 0, because there is no y appearing in this function, right. So, now my Euler-Lagrange equation reduces to the following equation, d dx of del del y prime of square root 1 plus y prime square, right, and this set equal to 0. So, or if we integrate this expression with respect to x, we see that what we get is del del y prime of 1 plus y prime square is equal to a constant, and this is also, once we differentiate this particular expression with respect to y prime, we see that this is y prime divided by 1 plus y prime square, right. So, after taking the necessary derivative, we see that this is also equal to the same constant, let us denote it by c. So, after simplifying this expression, we come to the conclusion, well, after solving for y prime, we come to the conclusion that y prime comes out to be another constant, let us say c 1, right, and then we can integrate this, expression to come to the result that the function y, which is the extremal, will be c 1 x plus c 2. Now, students are all familiar that this particular expression, this is the expression for a straight line, right. Now, we know that from the boundary condition, we know that y at 0 is 0 and y at 1 is 1. So, again Notice the boundary conditions here, and from here we get that the extremal y of x is given to be equal to x. So, the geodesics on a plane come out to be a straight line, and with the necessary boundary condition we can eliminate all the involved constants to come at a particular solution to the problem. Okay. So, then let us now so right now we have shown that the extremal is a straight line. We have not mentioned anything whether this extremal is maximum or minimum. We will later on show that this is a minimum. This is a minimum of the problem when we talk about the sufficient conditions of the functional for finding the extremal of the functional. Okay. So, then let us look at another example. We are given, again let us fix the boundary points, let us say x 0 y 0 is 0 0 and x 1 y 1 is 1 1, and we have to find the extremal, of the functional j of y, which is integral from 0 to 1 y prime square minus y square plus 2 x y dx, right. Okay. So, then again we use Euler Lagrange, and when we use Euler Lagrange equation we see that this is d dx of del f del y prime minus del y del f del y, which is also equal to d dx of 2 y prime, I am taking then all the necessary derivatives here, minus of minus 2 y plus 2 x, and we set this equal to 0 via through the Euler Lagrange, and we see that the equation that we reduce to is the following linear ODE, y prime y double prime plus y is equal to x, right. And this particular ODE has, this is a non homogeneous ODE. The homogeneous solution to this ODE will be a linear combination of cos and sine, and so I am directly using some of the results of the solution to ODEs. The particular solution to this problem will be y particular will be equal to x, right, and then we can combine to get the extremal of this functional. This is C1 cos x plus C2 sin x, the homogeneous solution plus the particular solution, right. Okay. So, from here all I have to do is to eliminate these constants by using the boundary conditions that we have. So, in particular I know that y of 0 is 0 and y of 1 is 1, and that leads to the fact that I get the first constant C1 is 0 and C2 comes out to be negative 1 by sine of 1. So, I get a particular extremal out of the family of extremals. Okay. So, that is how we do a typical simple case study of finding the extremal to any functional. Let us quickly wrap up this lecture by giving another quick example. Let us say I have a constant k. So, k is a positive constant and j is a functional which is given to be integral from 0 to pi y prime square minus k of y square dx with endpoints y of 0 equal to y of pi is equal to 0, right. So, we have to find the extremal, we have to find the extremal to this problem, right. So, again to find the extremal all I have to do is to plug the integrand in the Euler Lagrange equation and solve it, right. So, the extremal the extremal y is such that it must satisfy the Euler Lagrange d dx of, again I am just plugging in the necessary derivatives, I am taking the derivatives right away, plus 2 k y. So, students can do all the steps here. So, I am simplifying few steps. So, this is my Euler Lagrange equation. Okay. So, once we further simplify this ODE, we see that this reduces to y double prime plus k y is equal to 0, and I know since this is a homogeneous ODE, the solution will be a linear combination of cos and sine, right. And further we know that we are further given these boundary conditions. What we have is, it turns out that there are two cases for this. If suppose I have that square root of k is not an integer, my boundary condition will lead to only one solution, y of x is identically 0. Students can check that this is the only condition satisfying the boundary conditions here. And the second case that I have is that if k is an integer, it is an integer, then the only solution that I get is y is C2 sine of square root k x, right. So, I have infinitely many solutions in this case depending on the value C2, right. Okay. So, that wraps up our discussion in this lecture, and in the next lecture I am going to talk about further several cases of Euler Lagrange equations, and in particular I am going to do 4 case studies or 4 specific cases of the solution to the Euler Lagrange equation. Thank you very much for listening. Thanks a lot.